Okay, can we start the class? Hello.
Hi, sir. Good morning.
Hey, good morning. Can we start the class? Am I audible?
Yes, sir.
Okay, fine. Let's start the class. So today we will look at how to construct this code book, how to do this beamforming. So where were we in the last class? We were looking at the digital feedback. Just to give a recap. So what we said was the channel is estimated as this one. So after it's estimated, you have a code book. Code book will consist of multiple matrices that are known, whatever multiple entries that are known both at the transmitter and the receiver. Okay, and based on what you observe as your estimate, you pick out one element of the code book, and that is the index of that is transmitted to the base station. The base station also has this code book, so it again can reconstruct whatever that it knows what is the thing that has been sent, and it uses that as an approximation for the actual thing. Okay, is that fine? So this was the digital feedback setup. Okay, so now the question is, how do we make this code book? Okay, and what is meant by closeness and other things. Okay, so those are the things that we will discuss today. Okay, I mean, I have prepared. I mean, we will discuss only first what is meant by closeness criteria and other things today, and later class we will discuss on the construction of the code book. The construction of the code book may require us to look at some software part. I'll get back to that. Okay. So remember, our precoder is square root ES by NT. This is what we are going to transmit now. Square root ES by NT until F. Okay, is this the one? This is our what we are going to transmit. Just let me look at my notes 1 minute. Yeah, that's what we're going to transmit. And what is the other constraint that we have? We have the constraint that this is our precoder, and we have that norm of norm of f square 2 should be equal to 90. Okay, these are the two constraints. So precoder and the precoder is of the size what is a it's nt cross ns. Okay, with this background, let's set up. Okay. So first we will start with the case of beamforming. Okay. So when we do beamforming, essentially what do we do? I mean, we essentially transmit on the maximum eigenmode of H Hermitian H. Yes, this is so essentially the beamforming is nothing but the what do you say, the eigenvector corresponding to the maximum eigenvalue of H comma H. Okay. So now you have the transmitter. This is your transmitter, and similarly you have the receiver. There are multiple antennas. Of course, everything is multiple. Okay. And this estimated the channel H. Okay. So there are two things it can do. One thing is it can transmit the H value quantized. So one case is Rx can transmit, not transmit. Rx can send to the TX the quantized values of H. Okay, Once it sends the quantized values of h to the tx, what can tx do? Tx can compute h star h, and then from there compute the maximum eigen vector, and then use that for its precoding. Suppose Rx does this. So how much data should be transmitted? How much data? Okay. So if you how many complex numbers how much data means, I'll put it in terms of complex numbers. Okay, in terms of real number, in terms of reals. How many real numbers it has to transmit? Each real number can be in some 16-bit or whatever, how many bits you want. How many it has to transmit? It has to transmit 2 times nr times nt. Agree?
Yes, sir.
Okay. So on the other hand, if the Rx computes what is the maximum eigen mode of h star h, then how much data should it transmit? Can anyone tell me? How much data will it transmit?
220.
220, correct. 220. Technically, it will transmit 220 minus 1 because you also have this constraint. Nah? So you don't have to transmit all the quotients. You can reduce one quotient, but that's okay. Approximately 220 samples it has to sample. Okay. But in this second case, the Rx has to compute the product of h star h, and then what you say, and compute the eigen values for that. I mean, whatever the eigen modes for that. So now you can immediately see that there's a huge gap between these two. Okay.
Sir, I have a small doubt.
Narendra, is it you?
So, yes, sir. Yes.
Tell me.
So, is this analysis only for a SIMO system or for a general MIMO system?
No. I'm just giving you an example of beamforming. That's it.
Yes, sir. But why is it only in the maximum eigen mode of h star h? Is it lowest scenario?
Why? I'm saying you're using maximum eigen mode transmission.
Okay, sir. Clear.
Okay, I'm saying you're using maximum eigen mode transmission. That is one way of beamforming. Then what you do is, see, you have only one receiver. Okay, how do you do beamforming? If you do beamforming when you have multiple antennas at the receiver, the only way possible is maximum eigen mode. How else will you do? If you have CMO, if you have MISO or something, then it's easy. If you have MISO, then what do? You just multiply with the conjugate, normalized conjugate of the channel. But if you have MIMO, what is the way you do beamforming? The way you do beamforming is maximum eigen mode. Now that's what we learned.
Yes, sir. But I mean, why to transmit it only in the maximum eigen mode? We can select best of the eigen directions, no, sir?
Best of the eigen direction is the maximum. I mean, in terms of capacity maximization, it's we saw that's the best of the eigen modes is nothing but the maximum eigen value, no?
Yes, sir. But one thing I'm confused at maximum eigen mode, is it referring to only the maximum eigen value given eigen vector, or I mean some a few of total eigen directions?
No. So this is I mean that eigen vector corresponding to max eigenvalue. Only one.
Okay, sir. But why only one eigenvector, sir? We can choose other directions as well, no, sir?
So we actually saw this, na? We already also saw the optimality of this in low SNR regimes and other things, na?
Yes, sir. In low SNR, this is optimal, sir. But are we considering low SNR scenario?
When we say beamforming, it always means maximum eigenmode transmission.
Okay, sir.
Okay, so that is the convention. I mean, so if you don't do beamforming, there's so many other things you can do. You can do a better precoder. Okay, so I'm taking the example arbitrary precoders. I'll come. First, let's start with the example of beamforming. Okay, so in the beamforming, when you say beamforming, essentially it means you are transmitting only one spatial stream. Yes, and one spatial stream, and you focus all your energy in the maximum eigenmode so as to maximize your capacity.
Oh, now it's clear, sir. Thank you.
So I'm not saying you're using. I'm not. I'm considering the case of beamforming. When I say beamforming, it's maximum eigenmode beamforming. Okay, that's what I mean. We'll come to the arbitrary precoder case later. So what you are saying is arbitrary precoder. I mean, instead of transmitting the maximum eigenmode, you can transmit in multiple places, multiple things, however precoder you want. Okay.
Okay, sir.
Okay. So coming back to this, so I mean, you can see, I mean, this is a very simplified way of looking at things. You can see that you see a lot of savings in terms of the feedback channel. Agreed? Okay. So now the question is, so now you have a code book of beamforming vectors. Okay, so now you have to. So one thing is how do now you have a beam. So essentially, beamforming vector size is what? Okay, beamforming vector size is NT. Okay, so now you have to develop a code book. Okay, so develop a code book. F is equal to some F0, F1, all the way up to F. So the NF vectors, that's what we'll see. NF minus 1. Okay, so the cardinality of this thing is NF. Okay. Code book of size NF. Code book of size NF with all possible beamforming vectors. Okay. Okay. So to transmit an index of this beamforming vectors, how many bits do you require? How many bits do you require? You'll require log 2 of NF. Okay, those many bits have to be transmitted on the feedback. Okay, that's what you mean by sending an index of this code book. So the transmitter also will have the same code book. From there, it will reconstruct what it will know whether you sent this one or this one or this one, depending upon the index. If you send index 0, this is the one. If you send index NF, this is the one. Okay. Good. So now the question is, at the receiver, you have estimated H hat and computed the maximum eigenvector. I mean, so I'm using this thing in a very loose sense. A maximum eigen, there's nothing called a maximum eigenvector. So it's a vector eigenvector corresponding to the maximum eigenvalue. Okay, maximum eigenvector. So Vmax. Okay. So now the question is, what vector from F do you pick? So from what vector from F do you pick? Okay, so you have computed this Vmax. Let's assume that you have computed this Vmax in the receiver. So how do you pick up the vector? Okay, so one possibility is you say that your index is equal to argument norm of Vmax minus FL whole square. So FL belongs to F. Okay, so one possibility, this is one possibility. One possibility, what you're doing, you're trying to minimize the two norm distance to all the vectors here. Okay, do you understand this? Essentially, you're trying to minimize the Euclidean distance between this one and all the other vectors, and you're choosing the one which has the lowest, which is the closest in terms of Euclidean distance. Okay, so it turns out this will lead to lowest quantization error but not necessarily the best communication performance. Okay, in terms of capacity. In terms of capacity. Okay. So you understood. So one possibility, one simple possibility is you choose the one which has a smallest Euclidean distance from the V from Vmax. Okay, so that will always lead you to lowest quantization error. Okay, but that may not be the best in terms of actual improving and maximizing your capacity. Agree? Any question? Guys, you're understanding what I'm talking?
Yes, sir.
Okay, okay. Some feedback, please. I want to just know whether I'm audible or not. Also, sometimes the connection drops or something like that. So this is one option. Another most popular option is another second option is choose FL such that ergodic capacity is maximized. So what I mean is you choose your L hat to be argmax L expected value of log 2 of this is the capacity in beamforming. Okay, SNR times by NT norm of H times square. You understood?
Yes.
Okay. Okay. So if we want to simplify this and get in a little bit more, this is a very arbitrary metric. So we will simplify this. You understood the motivation for this? Essentially, I want to maximize my ergodic capacity. Okay. So since like Narendra pointed out, since beamforming is used at low SNR, what do we have? We have log 2 1 plus SNR will become. So so essentially at low SNR, the log of 1 plus x is equal to x. So this approximately is equal to maximizing this. This implies arg max expected value of you understood? Essentially, problems working with this is very much more difficult. So I'm just giving you the motivation for all this. So this is how the logical flow came when they were deriving all this. So they said that we'll maximize this part. So maximizing this, so now let's look at how do you maximize this? What does this imply in terms of distances? Okay. So one more thing that you observe is, let me just write this like this, an observation. For for any phase theta, I mean, this is very simple to see now. This is fine. So essentially, this implies optimal beamforming vector is not unique. Okay, in the sense that any rotation of the vector performs equally well. Okay. So now, so essentially, we have two constraints. One is the norm constraint, and the other is called the phase invariance. This is what is called phase invariance. This is called phase invariance. Okay. Okay. What do I want to do? I want to maximize Argmax picture cell. So now we define a new metric. We define a distortion. Okay. So we say D of the code book as a function of the code book is defined as SNR by NT, expected value of norm of H hat B max whole square, so minus maximum of FL belonging to the code book, norm of H hat. Okay. So what they're doing here is they are saying that if you just have send Vmax, you will get this is your whatever capacity. Because you are sending from the code book, this is the best you can do. What is the difference between these both? Okay, so this is always a non-negative quantity that you can observe, no? Because Vmax by definition is the most optimal thing. Actually, why can't it be negative? It can be negative. No, it can't be negative. Okay, it can't be negative. Okay, so this is always a non-negative quantity. This is always a non-negative quantity. Okay, so why don't you prove this? Prove. So did you understand this part to this point? Okay. Okay. So let L hat be the maximizer. Okay, so I can write my distortion of this code book as SNR by NT expected value of norm of H hat V max whole square minus norm of H hat EFL hat. This is fine. I'm just saying L hat be the maximizer. So now it's going to get a little bit, you have to follow this carefully. I'm going to write one step. First, look at this, and then we'll discuss. How did we get from here to here first? How is this equal to this? Can one of you tell me?
So we multiplied with the eigenvector, so that gave us the maximum eigenvalue corresponding to that eigenvector.
What happened to this NT? Very close. So I'll just show you this part. So norm of H hat V max will be equal to V Hermitian max H Hermitian H hat V max. So this is eigenvalue. So this will become lambda max times V max. It will become lambda max times V Hermitian max V max. This is equal to lambda max and the norm of V max whole square, which is equal to NT. So this is equal to NT times lambda max. Okay, so NT gets cancelled and you get lambda max. Okay, that is the motivation for this. What about this? What about that? How do you obtain that? Can you tell me? Can someone tell me? Okay, I will give you a small description of that. So again, you have H hat. I'm just going to do H hat F. Okay, I mean that's the same thing. You can. I don't want to write FL hat. You want to do? I'll just do it for some general matrix H. I'm going to do for HF. F is a scalar. Okay, this will be so. This is nothing but F Hermitian H Hermitian H F. If I know the eigenvalues of this, I can write H Hermitian H as sigma lambda I Vi Hermitian. Is that fine? Vi is eigenvalues. Do you think this is correct? I equal to 1 to whatever number n, some number n. If suppose someone gives you the eigenvalues of a matrix, eigenvalues and the eigenvectors of the matrix, can you write that matrix like this? As sum of multiple rank 1 matrices. Vi into Vi Hermitian is a rank 1 matrix, no? Agreed? Okay. Now you put F in that. So if you put F in that, so essentially F Hermitian, HF would be equal to sigma I equal to 1 to n lambda I F Hermitian Vi Hermitian F. Okay. So if you look at this is nothing but the norm of whatever V Hermitian F. This is nothing but this term is nothing but norm of Vi Hermitian. Okay, so that's how you get the second part. Okay, is this clear? Is it fine?
Yes, sir.
Okay, so now let's continue. So now if I just take this part and just copy into the next page. Okay, so this is less than or equal to. So if I neglect, so all of them lambda i's are all positive because it's a positive symmetrical matrix, no? And all other terms are positive. So I'll disregard all those eigenvalues and just keep the lambda max eigenvalue. So this is less than SNR times expected value of lambda max minus lambda max B star max of L hat square. This is scalar, sorry, this is scalar. Is this fine? So here I have used the fact for that for an IAD Rayleigh channel, for IAD H Hermitian, the lambda max values and the eigenvectors are independent. There's a result like that. For Wishart matrices, what happens is the eigenvalues and the eigenvectors are independent of each other. Okay, so they have used that result to obtain the independence of these two. Okay, so essentially it follows this. This follows from this step follows from eigenvalues and eigenvectors of complex Wishart matrix. Okay. I think there's some hand waving that's done here. I'm not very sure of that. I mean, I'm not very convinced that this is the argument, but this is the argument that they gave in the paper and the textbook. I'm not very convinced by the argument actually. Okay. But anyway, so this is what they do. And now what they do is they define this as, so now they write this as like SNR times they define a metric and d square of x. So, look at this difference. Any questions?
Sir, is this the definition of that closeness that I was asking last day?
Yes, this is what is going to become the closeness definition. Exactly. So instead of use, so essentially the first case what we saw was we could have used this. And this was the closeness definition if we use this one the first possible. But what I said, this is not a bad thing. It's a bad thing. So now we are going to use this as our closeness definition. This particular thing as the closeness definition. Okay. So this has a particular relevance. I'm going to tell you that in a minute. Okay. But did you understand the derivation?
Except for the penultimate step, I understood, sir.
So which step did you not understand this step?
Yes, that hand waving thing that somehow went beyond it.
What I mean, so essentially, except that expectation is split over two expectations, I just took lambda max common and just wrote this, and I then split up the expectation of A into B is equal to expectation of A into expectation of B. The argument is that the eigenvalues and eigenvectors of a complex Wishart matrix are independent. Okay, that's what they say, but there's an FL hack here. I don't know why that. Anyway, so there's a hand waving argument here that I'm not very clear of. Maybe I will also try to get a little bit, read a few more papers and understand what that argument is. Maybe I'm missing something at that point. But if you just consider that they are independent, then this is possible. This particular step is possible. And once that is possible, of course, this is just a redefinition of the distance. Okay. Okay. It turns out the d of xy is a distance metric on the set of all one-dimensional subspaces embedded within a NT-dimension space. Okay, so what this means is, okay, so for example, this is x and y. This is how, what dimensional space is this? There are two-dimensional space. This is R square. Okay, so what are all the one-dimensional spaces, subspaces in this? All the one-dimensional subspaces are any line that passes through the origin is a one-dimensional subspace. Yes, any line that can pass through this origin is a one-dimensional subspace. Yes. So now you take the collection of all these subspaces. Okay, so this is an example of uh, 1D subspaces in 2 dimension. In 2 dimension. Okay. So this is also called as a Grassmannian manifold. Okay, this is called a Grassmannian manifold. Grassmann manifold, and is denoted by G of nt comma 1. In this particular case, it's denoted by G of nt comma 1. In this case, this is example of G of 2 comma 1. Okay, in general, it's G of nt comma 1. Okay, so if you look at this manifold is nothing but the collection of all these subspaces. Okay, so if you look at in this particular example, the subspaces are parameterized by what parameter? The slope, the theta. They're parameterized by theta. So if I give theta, you know the subspace. There's a line at that angle which passes through this. So it turns out that this subspace itself is a smooth subspace, and you can define a distance in terms of this thing. So you define the distance between these two is nothing but the sine of the angle between these two. Okay, so that is what this distance dxy. If you think of this carefully, if you just consider x and y to be unit norm vectors, then d of xy is nothing but sine theta between those two vectors. Okay, so that is the distance between those two vectors. Okay, this is called a Grassmannian manifold, and dxy is a distance between the subspaces in that manifold. Okay, one more property of dxy is d of e power j theta x comma y d of e power j theta x y equal to d of x y. So this is not sine theta. Oh yeah, that's correct. That's correct. Sorry. Okay. So now, just coming back to what we have obtained this one. Huh? So you can also define a one more term, d min of f. D min of f is nothing but minimum of L comma L dash square root 1 minus so the distance. So the minimum pairwise distance between any two vectors in this subspace, in this manifold, any between okay, the minimum distance between any two subspaces in the Grassmannian manifold is this d min f. Okay, so what you can show is you can show that this. I'm not going to show this result. It's not that difficult, but you can read this in the paper. I'll tell you the paper. You can show that this is nothing but less than or equal to expected value of lambda max you will just cut and paste that instead of writing this over. If you look at this is nothing but the SNR that you get because of beam forming. This is the gap because of quantization. Okay. Okay, that's fine. I mean, how do you come from this step to this step? You guys think about it. It's not difficult. I can also share the paper maybe in the next class. I mean, I think you just have a look at it. It's not that difficult to come up with that answer. Okay. So in the next class, what we'll do is we'll look at generalized precoder. So here I was trying to motivate this whole Grassmannian packing, Grassmannian manifold with what do you say, with one-dimensional beamforming. Okay. In the next class, we'll look at generalized precoders and see if we can make any more sense out of them. Okay, that's what we're going to do in the next class. Fine. I'm going to stop now. You guys also have to sit down and read the textbook also once.